Hello viewers, I Nilofar welcomes you again to the second part of the chapter of Statistical Decision Theory. In this episode, we'll discuss the rest of the topics of the decision theory, such as decision problems using the expected payoff criteria, expected value of perfect information, that is EVPI, some non-probabilistic decision-making criteria such as Minimax criteria, Min criteria, Minimax regret criteria, and so on. We'll also discuss the decision tree approach in decision making. So let's see the first topic, that is non-probabilistic decision making criteria. The expected payoff criteria discussed in the previous section is probabilistic because it requires that a probability distributed to the state of nature. There are several criteria that do not require the assignment of probabilities in order to reach a decision. Some of the common non-probabilities criteria used in decision making under uncertainty are: the first one, Minimax criteria, Min criteria, and third one is Minimax regret criteria. Then we have Hurwicz criteria. Then the fifth one, we have Laplace criteria of equal likelihoods. In this section, we shall discuss these criteria in detail. The first one, Minimax criteria. To find the optimal act using the Minimax criteria, we determine the Minimax payoff associated with each act and choose the act that corresponds to the maximum of these maximum payoffs. The Minimax criteria is an optimistic one because it is based on the assumption or hope that the most favorable state of nature will occur. Maximum criteria. To find the optimal act using the maximum criteria, we determine the minimum payoff associated with each act and choose the act that corresponds to the maximum of these minimum payoffs. The maximum criteria is pessimistic because it is based on the assumption that the least favorable state of nature will occur. The other one is Minimax regret criteria. The Minimax regret criteria is based on the opportunity loss or regret table discussed in section decision making under uncertainty. To determine the optimal act using Minimax regret criteria, we determine the maximum opportunity loss, that is regret, associated with each act and chose the act that corresponds to the minimum of these maximum opportunity losses. The next one is Hurwicz criteria. The Minimax and Min criteria discussed earlier assume that the decision maker is either optimistic or pessimistic. A more realistic approach would, however, be to take into account the degree or index of optimism or pessimism of the decision maker in the process of decision making. If alpha constant lying between 0 and 1, degree of pessimism will be 1 minus alpha. To find the optimal act using Hurwicz criteria with alpha as a coefficient of optimism, we first determine the expected value, that is EV, for each act. This is given by EV for act is equal to alpha times m plus 1 plus alpha times m, where capital M is the maximum payoff and small m is the minimum payoff associated with the given act. We then chose the act which yields the highest expected value. Now that brings us to the next one, that is Laplace criteria of equal likelihoods. This criteria is based on the assumption that equal probability be assigned to each state of nature. Thus, if there are n states of nature, each can be assigned probability 1 by n of occurrence. Using these probabilities, we determine the expected monetary value for each act and chose the act which yields the highest expected monetary value. We'll see one example here. A fruit wholesaler buys cases of strawberries for rupees 200 each and sells them for rupees 500 each. Any case left would at the end of the day have a salvage value of only rupees 50. And analysis of past sales records reveals the following probability distribution for the daily number of cases sold. So that is daily sales like 10, 11, 12, 13. So probability associated with them will be 0.15, 0.25, 0.40 and 0.20. Now what is the optimum stock action for the fruit seller? Let's see the solution. Here the number of cases of strawberries purchased or stocked daily in an act and the daily demand of the cases is an event. That is a state of nature. Since the cost price of each case of strawberry is rupees 200 and its selling price is rupees 500, the fruit seller makes a profit of rupees 300 on each of the day, and hence the fruit seller would incur a loss of rupees 200 minus 50 or rupees 150 on each case unsold at the end of the day. Now conditional payoffs. Let M is equal to the number of cases bought or stocked by the fruit seller. Let N be the number of cases demanded per day. Then the fruit seller profit, that is the conditional payoff, that is the probability profit of Mn, can be obtained as explained below. That is case 1. When N is greater than or equal to M, that is the demand is more than the stock. In this case, all the stock cases are sold out and hence the conditional payoff is given by payoff Mn equals to rupees 300 M. Now that is N is greater than or equal to M. Now the next case is case 2, that is N lesser than M, that is the demand is less than the stock. Now in this case only N cases of strawberries are sold out and the remaining M minus N cases are left unsold. Hence at the end of the day the fruit seller's profit is given by P Mn equals to rupees 300 N minus 150 times M minus N. So that is equal to rupees 450 minus 150 M, where N is lesser than M. So let's make this equation number 2. Now combining the two cases we get Pmn equals to rupees 300 M. So if N is greater than or equal to M, and rupees 450 N minus 150 M when if N is lesser than M. So that will make the equation 3. Now using equation 3 we can obtain the payoff resulting from all possible stock or demand combinations. The payoffs are shown in table 1.1. Now the first part. To determine the optimum stock action, we apply the expected payoff criteria. The expected payoff or expected monetary value for any stock action is given by EMV for any stock exchange, that is equal to summation of probability times conditional payoff. So that the summation being taken over different states of nature. So EMV act of 10 cases will be rupees 0.15 times 3000 plus 0.25 times 3000 plus 0.4 times 3000 plus 0.20 times 3000. That is giving us rupees 3000. Now EMV for act 11 cases. So in this case rupee will have this rupees equal to rupees 0.15 times 2850 plus 0.25 times 3300 plus 0.40 times 3300 plus 0.20 times 3300. So that is giving us rupees 3300. Now EMV, that is the act for 12 cases. So this is equal to rupees 0.15 times 2700 plus 0.25 times 3150 plus 0.40 times 3600 plus 0.20 times 3600. So that is giving us rupees 3352.50. 0.15 times 2550 plus 0.25 times 3000 plus 0.440 times 3450 plus 0.20 times 3900. So this is giving us rupees 3292.50. Since EMV is maximum for the act stock 12 cases, therefore according to the EMV criteria, the optimum act is the stock 12 cases. Thus the fruit seller should stock 12 cases of the strawberries each day in order to get the best expected daily profit, which is rupees 3352.50. The next topic is expected value of perfect information. To understand the concept of expected value of perfect information, also referred to as EVPI, let us consider the preceding example again. The optimal stock action by the fruit seller in the preceding example was to stock 12 cases each day in order to get the highest possible average daily profit under the conditions given. This stock action was obtained under uncertainty using the expected payoff criteria. However, as long as uncertainty exists, there is the possibility that the expected payoff criteria may lead to the wrong course of action. Now suppose that the fruit seller in example 1 could remove all uncertainty from his problem by obtaining complete and accurate information about the future, called the perfect information. This does not mean that sales would not vary from 10 to 13 cases per day. Sales would still be 10 cases per day 15% of the time, 11 cases 25% of the time, 12 cases 40% of the time, and 13 cases 20% of the time. However, the perfect information, the retailer would know in advance how many cases were going to be called for each day. Under these circumstances, the fruit seller would stock today the exact number of cases buyers will want tomorrow. When sales were going to be 10 cases, the fruit seller would stock exactly 10 cases, thus realizing a profit of Rs 3000. For sales of 11 cases, the fruit seller would stock 11 cases and realize a profit of Rs 3300, and so on. Knowing the size of the market in advance for a particular day, the fruit seller chooses the stock action that will maximize his profit. We can now compute the expected profit with the perfect information, that is EPVI, also referred to as expected value under certainty, EVUC. To find the expected profit with the perfect information, we multiply the conditional profit, that is maximum for each state of nature, by the probability of the state, and then summing these products. Symbolically, EPPI is equal to summation of conditional profit, that is maximum for a state, times probability of the state, the summation being taken over different states of nature. In our example, the fruit seller's expected profit with the perfect information is EPPI equals to 0.15 times 3000 plus 0.25 times 3300 plus 0.40 times 3600 plus 0.20 times 3900. So this is giving us Rs 3495. This means that the fruit seller can earn average daily profit of Rs 3495 if he has perfect information about the future. However, this best expected daily profit without the perfect information was Rs 3352.50 as calculated earlier in the example 19. The difference between this expected value is called the value of perfect information. Symbolically, EVPI is equal to EPPI minus maximum EMV of AI. The expected value of perfect information in the case of fruit seller is EVPI equals to Rs 3495 minus Rs 3352.50. This is equal to Rs 142.50. The EVPI of Rs 142.50 is the maximum amount the fruit seller would be willing to pay per day for a perfect predictor, because that is the maximum amount by which he can increase his expected daily profits. Let's see the next example. A person wants to invest in one of the three alternative investment plans: stocks, bond, saving accounts. It is assumed that the person wishes to invest all of the fund in a plan. The conditional payoffs of the investment are based on three potential economic conditions, that is accelerated, normal, or slow growth. The payoff matrix is given below. Now determine the best investment plan using each of the following criteria. The first one Laplace, second Maximin, third Maximax, fourth Hurwicz. Coefficient of optimism alpha is equal to 0.6. Let's see the solution. First one, the Laplace criteria. According to Laplace criteria, we assign equal probability, that is 1 by 3, to each of the state of nature and then determine the expected monetary value EMV for each action and chose the action that yields the highest EMV. The computation of EMV for A1 stocks is equal to 1 by 3 times 10,000 plus 6,500 minus 4,000. This is equal to 12,500 by 3, which is equal to 4,166.67. Now EVM for A2, that is for bonds, is equal to 1 by 3 times 8,000 plus 6,000 plus 1,000, which is equal to 15,000 by 3, that is equal to 5,000. Now EMV for A3, that is for saving account, is equal to 1 by 3 times 5,000 plus 5,000 plus 5,000. This is equal to 15,000 by 3, which is again equal to 5,000. Now highest EMV is 5,000, which corresponds to Act A2 and A3. This, according to Laplace criteria, the best investment plan is to choose either Act A2, bonds, or Act A3, that is saving accounts. Let's see the next one, that is Maximin criteria. We first determine the minimum payoff associated with each action and then chose the action that corresponds to the maximum of these minimum payoffs. The minimum payoffs associated with different actions are shown in table 1.3 of column 5. The maximum of these minimum payoff is 5,000, which corresponds to Act A3. Now this, according to Maximin criteria, the best investment plan is to choose Act A3, that is saving account. Let's see the next one, third one, that is Maximax criteria. We first determine the maximum payoff associated with each action and then chose the action that corresponds to maximum of these maximum payoffs. The maximum payoffs associated with the different actions are shown in table 1.3 column 6. The maximum of these payoffs is 10,000, which corresponds to Act A1. This, according to Maximax criteria, the best investment plan is to choose Act A1, that is stocks. Let's see the next fourth one, that is Hurwicz criteria, with the coefficient of optimism alpha equals to 0.6. To find the investment plan using Hurwicz criteria with alpha as the coefficient of the optimism, we first determine the expected value EV for each act, which is given by EV act equals to alpha time maximum payoff plus 1 minus alpha times minimum payoff, and then chose the act which yields the highest expected value. Let's see the computation of EV with alpha equals to 0.6. So EV for Act A1 for stocks is equal to 0.6 times 10,000 plus 0.4 times minus 4,000. So this is giving us 4,400. Now EV for Act A2 for bonds is equal to 0.6 times 8,000 plus 0.4 times 1,000, which is equal to 5,200. The EV for Act A3 for saving accounts is equal to 0.6 times 5,000 plus 0.4 times 5,000, which is giving us 5,000. Since highest expected value corresponds to Act A2, therefore, according to Hurwicz criteria, with alpha 0.6, the best investment plan is to choose Act A2, that is bonds. So that brings us to the next topic, that is decision trees. A decision tree is a graphic model of a decision problem, whereby the sequence of alternate courses of action, state of nature, likely outcomes of various actions or state combination along with the conditional monetary values attached to these outcomes are depicted as if they are branches and sub-branches of a horizontal tree. Decision trees provide a useful tool in making decisions concerning investments, project management, personal and new product strategies. These trees are especially helpful when sequences of decisions are required to be made. Now let's see how to construct a decision tree. A decision tree is constructed starting from left and moving towards right. It is very important to maintain the proper time sequence when constructing a decision tree. The time in a decision tree flows from left to right. The following standard symbols are used to construct a decision tree. First one, squares are used to represent decision points, which are referred to as decision nodes or decision forks. A decision node represents a point where a decision needs to be made in the process. Each branch from a decision node represents a possible course of action or a decision alternative. Second, circles are used to represent chance events, which are referred to as chance nodes or change forks. A random event occurs at each node. The chance nodes are outside the control of the decision maker. Each branch emanating from chance node represents a possible state of nature or outcome. The portrait of a decision tree. Analyzing a decision tree, rollback technique. We have a decision tree can be analyzed using a technique called the rollback technique. The procedure in this technique starts from the rightmost column of the tree, that is from the top of the trees, and moves back to the left one column t at time to the root of the tree. Thus, in this rollback technique, by working from right to left, we make the future decision first and then roll them back to become the part of the earlier decisions. There are two rules directing this rollback procedure. First one, if we are analyzing a chance node, that is circle, we calculate its expected payoff by multiplying the expected payoff of each branch emanating from the node by probability of that branch and then summing these products. Second, if we are analyzing a decision node square, we compare the expected payoff of its branches and choose the alternative whose branch has the largest expected payoff. We record the choice on the decision tree by inserting a double dash as a barrier to those branches which have been rejected. Let's see an example. A person has two independent investments A and B available to him, but he can undertake only one at a time due to certain constraints. He can choose A first and then stop, or if A is successful then take B or vice versa. The probability of success of A is 0.6 while B it is 0.4. Both investments requires an initial capital outlay of rupees 10,000 and both return nothing if the venture is unsuccessful. Successful completion of A will return rupees 20,000 over cost and successful completion of B will return rupees 24,000 over cost. Draw an appropriate decision tree and determine the best strategy. So let's see how we are going to do the solution. The decision tree based on the given data is depicted in image 1.2. Now, having constructed the decision tree, we are now ready to analyze the problem by using the following rollback technique. We begin by considering the rightmost column of nodes, namely chance nodes F and G. For each chance node, we calculate its expected payoff EP as shown below. EP for node F is calculated as 0.4 times 24,000 plus 0.6 times minus 10,000, which is equal to 3,600. Now, EP for node G is calculated as 0.6 times 20,000 plus 0.4 times minus 10,000, which is equal to 8,000. These expected payoff are then placed above these nodes and which are showing in image 1.2. Next, we move one column to the left, which consists of decision nodes D and E. For each decision node, we compare the expected payoff of its branches and choose the alternative whose branch has the highest expected payoff. Thus, at node D, that is top alternative has EP equals to 0. except B alternative has EP equals to 3600. That implies 36 greater than 0, so choose the except B alternative at node E. Stop alternative has EP equals to 0, except A alternative has EP equals to 3600. So 8000 greater than 0, chose the except A alternative. The expected payoff for each chosen alternative is recorded in boldface over its decision nodes as shown in figure 1.2. The chosen alternative is also indicated by inserting a double dash as a barrier through each rejected branch. Next, moving one more column to the left brings us to chance nodes B and C. For each chance node, we calculate its expected payoff. So, EP for node B equals to 0.6 times 20,000 plus 3600 plus 0.4 times minus 10,000. So, this is equal to 10,160. Now, EP for node C is calculated as 0.4 times 24,000 plus 8,000 plus 0.6 times minus 10,000. So, that is equal to 6,800. These expected payoff are then placed over these nodes as shown in figure 1.2. Finally, we move left to node A, a decision node. For this node, we find that the except A alternative has EP equals to 10,160, except B alternative has EP equals to 6,800. So, 10,160 is greater than 6,800, so chose except A alternative. The expected payoff of 10,160 is recorded over the node A and a double dash is inserted to indicate the rejected branch as shown in figure 1.2. Following the open paths from left to right in figure 1.2 yields the following optimal strategy. The optimal strategy is accept investment A first. If A is unsuccessful, then accept B. So, finally, we have learned today the chapter of statistical decision theory. In this script, we have discussed uses of payoff and regret tables to analyze decision problems, solved a decision problem using the expected payoff criteria. We have also learned how to calculate expected value of perfect information EVPI and have illustrated some non-probabilistic decision making criteria such as Minimax criteria, Maximum criteria, Minimax regret criteria and so on. We have also discussed the decision tree approach in decision making. So, that finally brings us to the end of the session. We are finally ending here the last chapter of statistical decision theory, and that completes the subjects. So, have a great time. Thank you for watching and bye.
Thank you.